It is my pleasure to present Rob Graham, who lately has been in the news for scanning the internets in under 15 minutes. So I insist, since this is on S course, right, you might ask yourselves, well, what does the OS have to do with it? The OS has the TCP/IP stack, which Rob did not use. And this will be a story of how these things work, how they were designed to work, how they don't work, and how one must do something different to be very fast about packet traffic. So this is a story of architectures and design and parsers and fast internet scans, did I mention that? Rob?
So thank you. So the what my talk is about parsers, but at the top layer, because at the end of the day we parse network traffic as it arrives on the machine. But the parsers have implications going all the way down the network stack through the operating system. So I'm going to talk about the parser, but yet all the other things that lead into that. The main problem that I started these I have a series of presentations about is about scalability. Is that when you have, let's say, an Apache server, and you put it on the internet and it's working great, and you got thousands of people connecting to it at a time and it's working great. But after a while, the more connections you get, the performance starts dropping off. It's still a 1 gigabit server, so the traffic levels aren't the problem. The problem is the number of connections. When you have 10,000 or 100,000 or a million connections to the server, performance can go to zero. It's for every packet that arrives, it spends so much time processing that packet that it provides no useful services. And we tend to think that if we just buy a faster server and double the speed, that we'll get twice the performance. But that's not actually really what happens. So this red line represents an Apache server where I've doubled the speed of the processor. And for a small number of connections, I get double the performance as I expected. But my problem isn't the performance, it's scalability. I'm handling 5,000 connections, and I want to go to 10,000. But doubling the speed of the processor doesn't double the number of connections I can handle, and only increases connections by a small amount. So I'm not getting a doubling I expect thinking this way, I'm getting only 10% more performance the other way. And quadrupling or quintupling the processor speed, the graph is going way above here, and still every time I double the processor speed, I'm only getting a small incremental improvement in the number of connections. And this has been a problem for Linux, the whole LAMP, the whole Apache, Linux, MySQL stack, is that no matter how much I increase the speed of the CPU, or adding CPUs to the system, I'm not getting to this level I want, supporting the number of connections I want. And so that requires that we look at the problem, the whole Linux, Apache, MySQL, PHP stack, from a different perspective. From an operating system's point of view, the problem is very much watching what happens when a packet arrives. So this shows the whole Linux kernel, and this shows just the networking stack right here. And so we watch a packet arrive at the network driver, then it walks up the stack. And as it walks up the stack here, it accesses different data structures. Now, if you've got only 1,000 connections, all of these data structures are all in the CPU cache. When you have 1 million connections, all these data structures are out of the cache. And every time it's not in the cache, it's 1,000 instructions it could have been executing while it stops and waits for memory to arrive. So computationally, it's a very quick process to get from here to here. And Linux is very fast for a small number of connections, but because of these cache misses, this computation takes an enormous amount of time.
Well, when you say enormous, that's milliseconds, right?
Oh, microseconds.
Oh, first world problems.
So yeah, well, if it takes a microsecond, it means you're only doing 1 million packets per second. And 1 million packets per second for a server these days is quite small. So So a microsecond is what it could take, and that's unacceptably a long time. So like my scanner does 25 million packets per second, so I can't spend a microsecond per packet. That's 25 times too slow.
So world scale problems.
Yeah, internet scale problems. So I don't know, I haven't done the actual research yet. I've read the code, the Linux code, of watching do pointer chasing. And the packet arrives, it's got the packet descriptors, it goes and looks up the TCP control block, and then it's got to associate that with the file descriptor, socket handle, and then it's got to grab the thread information, and then in order to get that packet up into user mode memory. But there's other structures it has to consult along the way. So I don't know how many cache misses there are for each arriving packet. Seriously was suggesting that would be a good project, is to calculate how many cache misses per packet there are when you have 1 million concurrent connections and a packet arrives and it goes up the stack. How many cache misses do you have per packet?
So we could set up a proper scanning infrastructure, provided that the central college IT allows us, and then using hardware counters, which are present on the CPU, on the packet path, we do that, and that would make a nice project.
Actually, it just takes two machines with 10 gig Ethernet cards.
Well, we want the fun of scanning. But yeah, point taken.
So my home network is I've got this little rack about so high with 4 machines with 10 gig Ethernet cards, and they're really low-end machines. That's where I do all my testing. Let's look briefly at the packets. So we have the OSI model that we're all familiar with. You have the physical layer, which gets the bits onto the wire. It doesn't know what the bits are, it just knows the bits that it's sending. You have the local link layer, where it takes the bits and combines them into packets, or into frames. That's the terminology they use. And it gets the frames to the next hop, like to the local router. And only as far as the next hop in the chain. And then we have layer 3, the internet layer, which is what we tend to think of when we think of packets, with the remote IP address, and it gets the packet across the internet from here to Japan, and that's the internet layer. And then we have the layer 4, which is the transport layer, which gets, once it arrives at the local machine, it gets the packet to the proper application. And so for parsing, let's look at Wireshark. So Wireshark is, we also be using Wireshark for analyzing packets. This shows a typical connection. A SYN, a SYNAC, an ACK establishes a TCP connection. In this case, it's TLS, or SSL. So we get the client hello packet, and then the server sends back 3 packets in response, 1, 2, 3.
May I ask you to increase the font?
Okay. How do I?
Zoom. View zoom.
View zoom.
Control plus
There we
also
go.
works.
Control plus.
Maybe it's okay.
Is it big enough? You want bigger?
People in the back.
Bigger.
Is that good enough?
Go bigger. Yeah, unfortunately we have this issue.
And unfortunately, this is Mac OS, and it's well, it's the X Windows on Mac OS is kind of a. So the thing I wanted to stress was that it takes 3 packets for the SSL response to arrive. And what happens with those packets is they must be reassembled. It's sending back about 3 kilobytes of data that doesn't fit into 1 packet. So it's got to split the response, the certificates that it sends back, over 3 packets. And so Wireshark shows you this with this little thing down here that has a reassembly buffer, where quite separately from the packets, it's reassembled everything that was sent in those 3 packets into a large buffer that's 3,327 bytes long. And so one thing that TCP, the Linux network stack, does for you is it reassembles all that data for you. So when you write your application, your network software, as maybe doing you write your own version of OpenSSL, you're relying upon the Linux network stack to do all the reassembly for you underneath. And that's where scalability problems happen, is that you might not want the Linux stack to reassemble for you. Reassembling means that's got to keep track of packet buffers, and then at scale, all those extra packet buffers are cache misses. So because you're demanding the TCP stack to reassemble for you, you're causing all these extra problems that you would not otherwise think about when you're writing network software. And so that's where this idea of radical parsers comes in, is to redo how we're doing parsers. Instead of having a parser that relies upon the block of having all 3,000 bytes in memory, we think of a different way of doing it. So the way that when you take your networking class, you're taught to do parsers is, for example, if you're parsing the TCP IP header or the IP header, you cast a structure over the whole block of memory and then dereference from there. You can go backwards and forwards and so forth. The radical way is to do a streaming parser, which is a byte at a time. An incoming byte off the TCP connection, you do one byte sequentially, and you don't need to have the whole thing in memory. So, in class, what you're taught, I know which book you guys use at Dartmouth. Here's a standard one, the Unix network programming. And it teaches you to use this macro, N2HS, to swap bytes between how they appear in the network and how they appear in memory. And it assumes that you have both bytes in memory, that you've got a block that's all in memory, all been reassembled for you. And it doesn't really work when you're doing the byte by byte parsing. And here's how you should do it for byte by byte parsing, is you just grab the first byte, process it, and process the second byte. So in my experience with working with people, is that this has led to no end of confusion about byte ordering. People are confused about byte ordering, that never quite works. I've seen code from experts where they execute this multiple times because every time bytes appear out of order in some part of the code, they'll just add this again to it and swap them back again, and then they'll be confused later on, swap them again and again and again, and they're always confused. But if you think about a parser doing things the right way, if you do it this way, this works all the time. There's no if-defs, there's no ending conversions. You parse the external data here, you have the internal data here, and you don't swap the two by casting. So that's sort of an introduction to byte by byte parsing, but let's think in terms of a HTTP header. We're all familiar with HTTP and what it looks like on the wire. You get a simple header with get, the URL, the version, and then headers, which like host and stuff. So this is a small HTTP header. Now, if we think about byte by byte parser, parsing each of these bytes one at a time, I can construct a state machine to represent how I'm going to parse this HTTP header. So every input byte causes a transition, or in this case, it stays there for a while. Then a space causes it to transition to there, and then it's going to stay there for a while, parsing all the version bytes. It's going to hit the return here, and it's going to go to the end of line state, and so on. So we can construct a parser this way. 1 second while we can construct a parser that operates the same way. Is that it takes all the incoming bytes off the TCP stream, processes them one byte at a time through a state machine like this, and we've now parsed the HTTP header. And the way that this might look is something like this. Is I write my HTTP parser, I have a state variable representing each state in the state machine, and then I have an input byte. And I send this sequentially, each byte one at a time to the parser. And so I say, okay, switch whatever the current state is, like I'm currently at the URI, I get a space there, so I need to transition to the version, for example. And within this parser, here's how you construct, okay, so for each one of those states, I set a table for transitions. If the character is So if it's a new line, I need to transit to the new line state. If it's a white space, I go to the space state here for the method between the space between the URI and the method, or else I stay in my current state. So imagine if I write a web server using a state machine to parse it, and I send the request get space 5 billion more spaces than the rest of the HTTP header. If you're parsing with a state machine, you don't care, because you stay in the same state until you get the transition character. And this is actually how Microsoft IIS works. Microsoft has their own web server, Internet Information Server, and they parse the incoming HTTP header as a state machine. So over a TCP connection, you can send a get 5 billion spaces followed by the rest of the header, and it doesn't care. Because while it's in that state, processing those spaces, it just sits there and twirls. So we can actually write real-world parsers that are based upon this idea. Now if you do Apache, it doesn't do it that way. Apache buffers 64K worth of a block and then parses it.
In fact, there is an Apache issue that you could do a denial of service on it by sending in prodigious amounts of white space.
Right. So because that's one kind of state machine, was using the switch and case statements. Another state machine is just your traditional AO-Korzik or regex DFA. A DFA is called a deterministic finite automata. And so this shows an example of matching multiple patterns. So think of an intrusion detection system that has to search for the network traffic looking for signs of malicious activity. He'll search for multiple patterns. Like here, this is a search table for he, hers, his, he, she. Each byte causes a transition. So an incoming H causes transition from here to here. Then an E translates from here to here. And then so on and so forth to make the match. So we can process, if we're running let's say an intrusion detection system that wants to search for hostile methods. For example, this could be an intrusion detection system that would search for hostile methods like Gnutella. Gnutella is a peer-to-peer application that looks very much like HTTP, but in the method field, it's going to have a distinctive value. So we can search for that. So I can add the AO-Korzik byte-by-byte search method to my HTTP parser is doing a byte-by-byte parsing of HTTP. And so here's how I would add the searching into this. The thing about this is since it's doing a character at a time, I built a robust system that can do a complicated search of network traffic, but I only need a byte at a time for the input traffic and only 2 integers as my state. So if I'm tracking 10 million connections, I don't have that problem of having lots and lots of memory around that causing all those cache misses. I have only these 2 integers plus the input byte. So I've written an IDS that does that, and it works quite well. And I get lots of questions from people. For example, do you reassemble TCP? Back in the early days of intrusion detection systems that monitor the network, that was a big question because some didn't and some did. And I would get that question like, are you one of those that reassembles TCP? And the answer was no, I don't reassemble TCP. Yet I get effectively the same result because I'm using a state machine. A lot of people ask, does your code swap bytes correctly? And the answer is, well, no, I'm not swapping bytes, I'm processing them one at a time. I'm not ever swapping them around, I'm just, in the process of processing them, they're always in the right order. And there's other questions about like data normalization and stuff that all get solved by the state machine. So the answer is no, but the answer the real answer to their question was yes, and get the same results.
So there is an issue with not reassembling TCP. The standard IDS bypasses,
Right.
That go back to 1998 and the Pachak and Newsham tricks, which were really very simple. What if you send 2 copies of every TCP segment? What would 2 identical copies? which one would an operating system take? A Windows would take each first. Linux would take each second, or
Right.
vice versa.
Right, to do non-identical copies.
Not
There's
identical.
one byte.
Exactly. Identical.
Except for one thing.
That's right. Identical except for the thing that you want to hide.
Right.
So the streams reassembled at the IDS and at the target were different. The stream reassembled at the IDS was innocent looking, and the stream that reassembled at the target contained the attack.
Right.
So what can you do with that?
Well, with state machines, since you have so little amount of memory per stream, you can simply fork the stream. You can now, when you get an ambiguous situation, instead of dropping one packet or the other, you can make a copy of the streams. So now you're processing every input packet on that stream twice. Once the way Windows does it, discarding the first packet, and once the way Linux does it, discarding the second packet.
That's interesting. So you could work around ambiguities and protocols
Right.
by forking your stream. How do you merge them back?
Well, you're sort of forked from that point on. So now you're for that stream, you're now forked permanently.
For the rest of the stream.
Until the stream is done, at which point you destroy the fork.
Right, you destroy both streams.
Interesting.
But that gives you a rather nasty DDoS attack on the IDS because the IDS has to keep exponential memory if it never discards the stream.
Well, no, because it only forks it once. Once it's the Windows method. So not.
Julian's saying you keep sending ambiguous packets.
Well, yeah, but
If you
but
fork
it's
on every one of them.
but you only
Okay,
you only fork it the
keep
first
checking.
one, and then from then on it's ambiguous.
Yeah,
I mean,
you will need knowledge of the target that you're protecting. And of course, there has been a paper.
No, you don't need target.
He's saying on one fork you're gonna just parse them all as Windows, and on the other fork you're gonna
Yes.
parse them all
Always
as
just
Linux.
Exactly, and you'll have to
and you don't care what the target is.
Yeah. So as long as you don't have multiple discrepancies that you
So yeah, so it ends up that you can. There's a certain DOS that you can create 5 different ambiguous. So it's got to fork it 5 times, and so you're doing 5 times the amount of processing for your connection. Overall, that's actually not a bad thing. There's not a lot of extra work involved because you can't send enough traffic to DOS me.
So it's linear.
Right.
It's not exponential. Oh, that's an interesting observation.
And so we get that property, we can do that forking because we're keeping such a low amount of state per stream that we can just say, hey, we just forked the stream. It's not kilobytes, it's just an extra couple hundred bytes. So, yeah, so keeping that low state means there's not much memory involved, you don't need to reassemble TCP. Other things happen too, like buffer overflows tend not to happen. So when you do these block mode parsers, what you tend to do a lot is to make copies of buffers within the blocks. But for processing a byte at a time, we tend not to buffer things. And therefore, we tend not to have buffer overflow problems.
How many buffers exist in a normal packet traversal through the classic TCP/IP stack?
Well, so there's the stack, but let's take a look at parsing what you would need to do for TLS. So TLS, during the hello process, the server sends you their certificate. And here's an example of a certificate. And so we have a byte here, that's the content type, version, length, and here's a length of a sublength within this field. So we have 3,327 bytes, which is the first few bytes plus a buffer inside of it, which is just a few bytes shorter, 3,322. And most parsers will take this entire, once they grab this length field, they'll malloc 3,322 bytes to then store the rest of this in it. So every time we come across something like this, it tends to be a buffer that people memcopy, malloc and memcopy into. And as we go down the certificate, with each layer we go down here, going this way, is yet another 3,315 byte field. And within that, there's a certificate that's 1,377 bytes, and so on and so forth. There's a signed certificate, and here's a field, the signature, and here's a OID, it says it's SHA with RSA encryption, and so on and so forth. So every time we walk down the structure, we are probably allocating bytes and having potential for a buffer overflow.
So even though the TCP/IP stack at the lowest layers tries to keep the packet in one buffer and merely points the pointer, here, if I'm a packet, right? Starting with a Ethernet, right? So this is how I sit in memory. The Ethernet layer knows this much of me and has 2 pointers. This is the start of the Ethernet, this is the end. The IP layer looks at this part of me, and a TCP, at this part of me, or something like that. So I'm out of, as usual, somebody nicely cleaned the board and cleaned away the markers as well. Thank you. And this is not a permanent marker. Very good. Yeah, the usual.
It's a very temporary one.
Definitely not permanent.
Yeah, definitely not permanent. So anyway, yeah, we're for the analogy then. So you, right? Oh God, this is so
Hand
good.
me that green marker.
Yes.
Leave for the next person.
So
We're dropping
Ethernet,
it off in the English department.
Ether, IP, TCP, and then payload, say HTTP, maybe SSL, right? So when this arrives from the actual network card, by DMA, into memory, the structure which receives it, the SK, so-called SK buff, will keep that packet at least for this long in the same place. And the Ethernet parser will work between these 2 pointers, and then the IP parser will work between these 2 pointers, and the TCP parser will work between these 2 pointers. And after that, as Rob is saying, there starts a free-for-all. All of this careful consideration of let's keep a packet just where the card gave us that packet. Yeah, all of that is thrown away, and you start allocating memory all over the place.
Reckless abandon.
Yeah, with reckless abandon, exactly. And you've got your data structures, all over the place. They may be in a special heap, which may be a slab, depending on the protocol, but they may not be. In fact, it would make a good project to understand the memory patterns of something as common as SSL TLS.
So back in the early days of Linux, they would make a copy of the packet quite often. So every time they process a new header, they'd essentially make a copy of the packet. So this movement to just work with the pointers was called zero copy. But there's 2 flaws to that. One of which happens here. The packets arrive on what's called a ring buffer, and for the driver, so the hardware. And when the packet arrived, instead of copying, it used to be the packet would be here, and then they would make a copy down to here. And that would be the first copy that would happen. And they got rid of that copy, and they now just take the pointer out of the ring buffer and just point it and just take the pointer onto the system. But they've got to then allocate over here something to replace that packet. And as it turns out, this allocation step is more costly than if they just make a copy. So it's actually, sometimes making a copy is actually a good thing. Yeah, and then here, to the user mode memory, when you do a receive function call, you're copying from what was in the kernel mode here into user mode. So you still always have this copy, always happens regardless, in your normal sockets programming.
Yeah, it's worth keeping in mind that copies themselves are really cheap. Allocation is expensive.
Right. Of course, now the way Linux was in the old days, though, it made lots of copies.
Yeah.
So it didn't really need to make.
Well, we have seen the VMEM allocation and the complicated mechanism underneath, and the extents to which you need to go to manage just the ranges of integers as a resource. which VMem finally abstracted away.
So one question people have about this byte by byte method is the performance. Because we're taught that if we handle like mem copies in bulk, things are very fast. But if we do it byte by byte, that's traditionally thought of as very slow. So one thing we should look at is the theoretical speed of how fast parsers can work off of network traffic. So if we have a 1 gigabit network connection, how fast is my parser parsing the incoming network traffic? Well, for a regex or an AHO core is in a DFA format, this is how they're processed. You have a state, you have a table with the current state, and then the incoming byte causes a transition in the state table. And this maps very cleanly on x86 into one instruction. So the question is, how fast does this instruction run? It's going to run once per byte. And we can model this by creating just a sequence of instructions, and we set them all to 0, basically. Or set EAX to point to EAX, there's no real transition. It turns out the speed of how fast this runs is for every one of these instructions takes 1 L1 cache hit. Because x86 is really great at processing many things at once, many instructions at once, but they have to be independent. The problem with this is that each new instruction, the value of EAX depends upon, or the value of EAX here depends upon what it was here. So we have to wait for this whole instruction cycle to complete, which takes reading from the L1 cache, doing the processing, and then storing the result in EAX. So it's 1 L1 cache hit.
Does your whole state table really fit in L1?
My whole state table what?
Your whole state table really fits in L1?
In practice, yes, because remember, it's what's on the network and not what's in your state table. So your whole state table, no, it doesn't fit in L1. But what will appear across the network almost always does.
So the footprint,
The footprint.
Of the language that comes in, that you're recognizing, fits in.
Right. So you have all these cases that never happen in the real world. Now, it is one way to view.
How big is the full state table?
Well, it depends on what I'm doing, but it can be many megabytes in size. And yeah, it can be larger than the L3 cache in some cases. So yeah, so you want to sort your fields to have the ones, because almost always what happens is you get to an error state that goes back to the state 0. And that's, so you have all those, you have a cluster of states that you spend a lot of time with and then no time with the rest of the states. So like a Core 2 Duo or whatever, the older processors had a 3 hertz cache. It would take 3 clock cycles for you to read from the L1 cache, and they ran at 3 gigahertz, which is easy math because that means it's 1 gigabytes per second or 8 gigabits per second. So that means the theoretical speed for an IDS, for example, it searches the network traffic for patterns, is 8 gigabits per second per CPU core that has this property. Newer CPUs, by the way, have slower caches. So actually the speed goes down, but then you've got hyper-threading so that you can do 2 at a time, so the speed goes up. So that's for where it's data-driven. In the switch case statement, things are a little bit different. Each case, the CPU, if it can predict the branch for each byte that comes in, it's 0 clock cycles in theory. If it can't predict the branch, it's 15 clock cycles. So the speed goes down by quite a lot to only a couple gigabits per second per core if you've got lots of branch misprediction. So when you write these switch case statements, you write them in such a way that the branch misprediction doesn't hit you. Also, we model this with the functions I wrote, processing 1 byte at a time. But in practice, when you write your state machines, you say, well, at this state, I'm going to grab as many bytes as I can. And you process as much of the block as exists at that time. It may be fragmented, so you only get part of the block, but at least you can grab multiple bytes at a time. So even though we're thinking in terms of 1 byte and how fast that is, in practice, we can grab multiple bytes. So I wrote code to actually play with. You don't know how to increase this font, do you?
Try the same.
Apple Plus.
Or Apple.
Apple Plus.
Apple Plus.
Apple Plus.
No?
View
View, yeah.
Zoom.
View
You
zoom.
get the
You go
Change
to
the
Xcode preferences.
Okay, yeah.
Preferences.
magnifier on the sex.
Oh, yeah, there is.
Preferences, text editing,
Too complex.
Oh, fonts and colors. There.
fonts and
There
colors,
should be a display. Actually, that's huge.
There should be a better X.
plain text.
Uh-huh. Okay, yes, yes, you're almost there. Make it something huge.
Okay.
Oh.
It's hideous, but you can read it.
That's not, that's.
So you understand English.
So only some constructs changed size, not others.
Oh, there's
Can you understand identifier only C?
There's a presentation theme that made doing what.
Yeah.
exactly.
Okay.
All right.
That's what you want.
Okay, let's try it.
Make it larger. I mean, since much of this class was reading source code, we've had this problem.
So what I've written here is two functions. There's a main function that reads in from standard in, and then just gets C, get the next byte, and then sends it to my HTTP parser. And then I wrote my HTTP parser, which is just your bunch of states. Start, you got the start state, you got the method, you got the, so as I described in my presentation, is then each state processes, does something with the character, like if it's an end, it goes to the end of line state, so on and so forth. And then version, end of line, the name, as they say, of names, separated by a colon and value as part of the rest of the headers, and so on and so forth. So this is, in the practical thing is you could write from this, you could write a web server, you could write a intrusion detection system, you could write all sorts of stuff that would need to process an HTTP header. And this runs really, really fast at many gigabits per second, assuming that the input comes in at that speed. Now in practice, you wouldn't want to actually call the function with 1 byte at a time. You'd probably have a buff, and then length, and then for the here you'd say, well, for I equals 0, I is less than length, I plus plus, and then char C equals buffs of I, and then you have your switch case statement. So in reality you're really going to process many bytes at a time, but conceptually we're still just doing the byte at a time parser.
In practice, what sort of define, like, how many bytes is usually good, and what would sort of change that? Is this a caching thing, or is it?
Well, you would process many bytes at a time, but in your for example, in your method state, instead of saying, okay, look at this byte, I might say, well, process all the bytes in the method.
Okay.
So Intel x86 has a nice instruction for text parsing, where you can say something like, go grab all the bytes that I have that are alphanumeric, and just go grab it, find the length in one instruction, so one clock cycle, up to 16 bytes. And so you then process them. And if that didn't complete the state to transition, you just leave the function and then get called again. You're still in the same state. So you're processing many bytes at a time, potentially in each state. In practice, what you do is you focus on the states where there's a performance hit, and you just ignore the rest of the states. So this is the HTTP parser. So this is up on GitHub somewhere.
Well, if you should choose this for your project, we'll obviously give you all the pointers.
So that's just a simple program. That is not real world, right? So here's my port scanner. There's a lot of files here, but most of them are pretty small. So my port scanner sends out SYN packets, and if it gets a SYN-ACK, it'll create its own TCP connection. And the thing about that is, in this model, we have 0 copy here, but you've got, IP reassembly buffers here, you've got the TCP control block over here, Before it sends to user mode, you got to go through the thread entries there, and you got also got a file descriptor, D for the socket. So all these extra buffers are things you have to consult when you get all your cache misses. So in my code, this mass scanner, it can scan the entire internet in 15 minutes, as Sergey said. It does its own TCP stack, where all of these data structures that it needs for processing SSL and stuff, they're all in one buffer. So there's only one L1 or one memory cache miss when the packet arrives, and that's it. It's all there. And so
Yeah, and one TLB entry.
no, it's less than that because if you use huge buffers and stuff, it's
Well, critically, they're not on multiple ones.
They amortize.
yeah. So so I have two parsers, one for the SSL layer, which is a layer, and then one for the X.509 certificates. And so this is a real world problem. So what I want out of X.509 is I want to hunt down through the certificate. Instead of downloading the entire certificate, I want to get to just this right here. So the website I went to was googleusercontent.com. And I just started up Wireshark, went to Google, and grabbed the first SSL session, that was it. So what my scanner does is, when it scans the internet, connects to every website, it doesn't know who it's connecting to. It just knows, hey, I'm establishing an SSL connection. So the scanner reports back just the name of the server as is in the SSL certificate. So I do all this work. I've got this TCP stack, an SSL parser, an X.509 certificate parser that parses all this stuff, and all I want is just this one name, just whatever host it is I'm connected to. And so I use a state machine parser because all that parsing is just all in the same. It's about 512 bytes of memory per TCP connections. I have 10 million connections open, and it's only 5 gigabytes of RAM. So, and the parser is not pretty. So to start with, I got a lot of states. Because I got all these different fields within the X.509 certificate. And there's a lot of them. And then, and there's a kludge. But then I do have this long case statement. And a lot of states are processed the same. So for example, in this state right here, all these states are processed the same. And so that collapses a lot of the code.
So my question is, how do you debug that? Because what you'd like to do is to generate that code from some definition of the data. X509 uses ASN1 encoding.
Right.
ASN1 was meant to be a standard that you could generate code from. Instead, it has 5 kinds of strings, 3 kinds of integers, or vice versa, and many ambiguities. So it's not a good deal to try to parse ASN1 unless you have to, unless you're already parsing a protocol where it's entrenched. But there is always the question of how do you debug that code?
Yeah. Well, one thing is, I don't know, a lot of people don't use source level debuggers. But when you have a source level debugger, it's actually not too hard. You just set your breakpoint to be here at the code, and you start a scan, for example, scan to a known server, and then you hit the breakpoint. And then you just step through it byte by byte, as you're going through the certificate, byte by byte. Actually, this has got a little self-test section in here where I just dumped in.
So essentially, you test the smaller parts of this parser online.
Actually, I've got a test somewhere here where I've got a certificate of just the code of a certificate, just bytes, just file somewhere. I don't know where. It should be here somewhere.
That's interesting question.
Well, yes, that's exactly it.
Alright, well, generate, take a server, generate lots of certificates and corrupt ones and stuff. By the way, I've got a $100 reward if you could find a bug in this, a vulnerability that will crash it, or take control of it. So that's how I debug. Is like you spend $100, you offer $100 reward.
I will match that with a high pass.
So, and by the way, I just slammed this together really fast. So I put this code together really fast. So it's not, the chance of having a vulnerability here is quite high. So don't think that like I'm an expert, you'll never find one. No, I think you'll find one if you look hard enough.
Just in the interest of someone doing this, I'll take in another 100.
So yeah, so ASM.1 is known to be difficult to parse, and that everyone who tries to parse it has a vulnerability in the code, and you should never do your own parser for it, by the way. I say as someone, of course, who's written my own parser. So yeah, so I parse down, and then I get to the subject name, and I pull it out, and there I am. I forget where it is in here, so it's in here somewhere. So yeah, it's this quite ugly code. So and that's the issue with these state machine parsers, is that if you're not familiar with them, it's really hard to grasp what's going on with them because you've never experienced this before. But on the other hand, once you start debugging this and just start going byte by byte through the code, it's actually quite easy.
So what you could say is that you are testing it by element, by sub-parser, and going down from larger blocks of code that parse more complicated structures to smaller that parse less complicated structures. So in a sense, you're debugging it, I will not say in parser combinator style, but you are debugging it in a constructive style that builds up from elementary parsers to larger parsers, which is an interesting observation. Again.
So the SSL parser, that was the XF59 parser. The SSL parser is a little bit easier to debug. I've got this macro here drop down, and all it does is increment I and compare against the length and then exit out early. But what happens is when you step through the code, you pretty much step through linearly. So you're walking through, for every byte in the packet, you go forward to the next state. And so actually you can put Wireshark on one side and then debugger on the other side. And you can, with Wireshark, you can go field by field and then go through the parser field by field, and it all matches up quite cleanly.
So in fact, you could match that up with the dtrace and see where in your code, where in your state you are, just as a matter of a dtrace script.
Okay.
Right? Because that's how you would step. You would instrument your eat the byte, and you would instrument your transitions, and you would get a path through the code charted by dtrace. So that way you don't even need to step it through the debugger. You can generate the path using dtrace as a tracer. All the more so because you know all of your abstractions and all of your subparts. So you know exactly where to put dtrace probes.
So actually I can debug it right now. So I hit go. It took a while because I got all this static analysis stuff turned on, so it takes a while to compile. But so I have a self-test in the code. It's got certificates that parses in the self-test. So we can just hit, what's the simple step in Mac OS? I don't debug much on Mac on this, so I don't know it so well. So yeah, so you just step through it one byte at a time. Now the way that this parser is structured is kind of annoying because it's always going to go back up to the top to the next state. So I'm in the length state. So I'm processing the length field. And now, okay, I've exited the length field by incrementing the state variables, and now I'm going to go to the length of the length. So it's the ASM1 thing. That length of lengths and stuff.
Do you have length of the length of the length?
No, just length of the length. So now it's that thing, and then I go down to here. I'm at this state, go to the next state there, and so forth. So this is really a kind of annoying kind of debugging. Now I've got the next field, it has its own length field, so back in the length. So a lot of, ASM1, it codes every field with the length. So I'm going to spend a lot of time in this state here dealing with the length, and then the length of the length, and then that's ASM1 for you. So anyway, so that's how you would debug this, is that you would just step through the code, and it's not as onerous as it looks, once you get used to it.
Well, as usual, you want to generate both your code and your debugging from your data definitions, right? So you could generate a test script from a data definition as well.
The thing with ASM1 though is you really want to generate lots of bad ASM1 packets that are intentionally corrupt. One way I've done it in the past is I just take the same certificate and I just randomly set a bit, flip a bit, and then run the parser. Then flip another bit, flip it back, then another random bit, run the parser. I keep doing that.
That's fuzzing.
Fuzzing. And if there's no graphs, I call it good and ship it. There's lots of other stuff. There's lots of things within the ASM1 parser. Yeah, back to that thing. So within any field, you can have yet another field underneath it, which will kind of disturb your parser. Or you could be missing a field, and so there's lots and lots of other things that can go wrong with the parser. So, and the reason why I need more than just one integer, I need more than one integer state, is that each level down I go down this tree requires I keep the state of the tree above it. So in an SSL certificate, there's 7 layers that I can go down to get to my string. So therefore, I need to keep 7 layers of stuff around. One thing to note about this is the way this string is done is this is an ASM1 structure. It has 2 fields within it, essentially. One of which is a string saying what this field is, which is the common name, meaning server name, followed by the string itself. So I need to match this. I need to test that this value is 2.5.4.3. So the typical way of writing a parser is you would buffer this, memcopy this into another buffer, process it, analyze it, do all your stuff within its own buffer, and then whatever, because you're backtracking. I can't backtrack. So I have to match this while I'm doing the whole parsing.
So you're already past the DFA and you're into a stack-based push-down.
Right. And I call it a DFA because logically that's what it is. So I have this AO Corsic parser I call SMAC. It's my little AO Corsic machine. And that's how I process this. That name field is, I then do a byte by byte match of that sequence. So I don't need to buffer that field separately. I can just do the match in line with another state machine. It's another layer down for the pattern match. So I match the OID. If I get a result, I store it off somewhere. And then later on, I process that field. I know that, hey, this is a common name. This is the field I want. Then I'm going to copy this and then report on my little scanner. So, by the way, the reason I wrote this way, instead of using like OpenSSL, is partly for the scalability, but partly also because it's a useful real-world example of why you might want to use a state machine parser. That's why I went through all this extra trouble. It really is just overkill.
Have you tested them for performance? How much faster is yours than the OpenSSL ones?
Well, OpenSSL requires I buffer the entire 3 kilobytes. So SSL will not work until I've buffered everything. And if I were to try to do that at 10 million connections, that's going to be, what, 3 terabytes of memory I need in RAM?
I see. So then another question. How much of the functionality are you sacrificing? Could you build a functional SSL client on this approach?
I haven't tried it, but I think you can. there's more things that you need to start doing, like you need to take the MD5 or the SHA-1 hash of the certificate stuff, which requires some state memory, so it requires, you're going to increase the amount of memory you need, but yeah, I don't think we need as much as OpenSSL does.
Interesting. So we're coming up on our time.
Let me see if there's anything else. I forget. Yeah, that was it.
Questions?
You looked at using something like Regal to generate your state machines.
Yeah,
Um,
I'm too lazy.
okay.
You might want to say what Regal is.
Regal is a state machine generator that is probably most famously used in the Mongrel parser, which is the HTTP parser behind pretty much every single Ruby app that's been deployed in the last 4 or 5 years.
You mentioned early ordering the states, how that's important for cache clearance.
Right,
How do you do that
manually.
manually? So there's a huge volume of literature in linear algebra about how to do that problem correctly.
There probably is.
Yeah, there is a really good hacker by the name of Dmitry Nedospasov, and he was asked at some point, well, which algorithm do you use to, and he answered, well, I call it the Dmitry algorithm.
I mean, manually works well for a few hundred states. You know, a million states. Then it's
Right, well, the thing is even very large state machines tend to have only a few states that you can keep within your head anyway.
yeah, to be more
And that-
precise, it works well when you have a few hundred commonly used states.
And you always have just less than 100 commonly used states. So I've never had anything where it's larger than that. But yeah, the way we really want to do is like monitor the network traffic and then see what the real states are being used in the real world, and yada yada yada. And that's what's made.
I mean, it is precisely a source matrix ordering.
Yeah. So, but also for Regal, one of the big reasons I kind of avoid it is I hate the dependency chains, the dependency hell. That if you get a project and you try to compile it, like trying to compile Ruby from scratch for your machine, it takes forever.
Right. Oh,
And so to compile this program takes no effort because there's no dependencies except for the pcap.
So the solution to that for Regal is you pre-generate the file in your
Right.
distributions.
Right, and that works. But yeah, I hate dependency, so this.
Fair enough. I suppose the other question is, have you looked into any of the, or turns out that implementing a state machine in code is not entirely different from implementing a virtual machine. And so there's a bunch of neat techniques like direct threaded code and so on that results in significantly better performance.
I'm already way faster than everyone else, so I don't really look into much to improve it further.
How do you compare to academic projects like ZMAP?
Like ZMAP does a gigabit per second parser, so Masscan does 10 gigabits per second. ZMAP has a limitation of only a few thousand concurrent connections, whereas Masscan has 10 million concurrent connections.
Do you know if they use the TCP/IP stack? Or
They use the Linux TCP/IP stack. They wrote their own kernel mode driver that once they get back a SYNAC from a connection, they have a tiny little driver that says, okay, create a connection in the TCP kernel from user space, create a connection rather than from the actual packets that arrived, which will then behave from that point on as a normal TCP connection. Then they use that.
This is interesting. So that would make another good project. ZMAP has been a much publicized academic attempt at scanning the entire internet, performance scanning. Comparing its architecture with this and finding the performance bottlenecks and describing them comprehensively would make a nice project.
It's also worth noting that for finite state machines with relatively small numbers of states, direct threading is rarely a win on more modern architectures with equal branch predictors.
I would like you to say then a few words about direct threading. Stand up.
Well, do you want to talk about it since you brought it up?
I used the wrong term. The technique that I was looking at is having the dispatch at the end of every
Right.
case.
Yeah. So the benefit of putting a dispatch at the end of every case is that the branch predictor has more information if you have common like diagram or trigram frequencies where this state often follows after this other state. The branch predictor can predict each of those branches with very high probability. But the thing is that the branch history table on more modern x86 processors kind of has that built in already. So if you have even just a single branch position, you can get pretty good prediction from that, and you get slightly smaller code size because you don't have the extra branch at the end of everything. So at least I have seen a lot of cases recently where doing that turned out to be at best break even, if not a loss.
Okay. And the place to start reading about this would be optimization manuals by.
I mean, for that technique specifically, the guy who does the LuaJIT has written the most interesting things about that technique.
Could you send me a link?
Yes.
I'll forward
Yeah.
it to the class. Alrighty then. Thank you for attending. This was a very interesting conversation. When we let the speaker speak. Our Wednesday class will be devoted to hypervisors and the tricks that exist there.